Alright, welcome again. I'm gonna close this to our stream. I just want to start off. I sat down for the first time today. Oh, and I gotta turn the volume off again. Okay, so I just want to start off because I just sat down for the first time today, all day, to stream, and I sat for like a minute or two just to get the slides together, but I just caught my breath from chasing my kids around, and my kids were out of control today. So this is like Corona Chronicles 3.0, wild things that went on in my house. Today we painted, and we did a whole lot of Play-Doh, and my house looks like a bomb went off. We did not trap the leprechaun, in case anyone was wondering, because I know that was like a big thing yesterday. We were making leprechaun traps. That did not happen. He escaped, so we have leprechaun trap 2.0. And then there were 1,000 questions that my daughter had today that she just like wouldn't stop asking me. Completely ridiculous, out of the blue questions. And I found this online, and I want to play this for you because this is kind of what it's like being in my house right now with all my kids being trapped inside and asking 1,000 questions. So I'm just going to play this for you. Just a little humor. 40 seconds, and then we're going to get into chemistry. So that's kind of that's kind of what it's like being in my house. It never ends. I'm gonna minimize this, and before we get into chem, I just want to have you guys give me the affirmative on the sidebar that you can hear me, you can see everything, and we're gonna head back into equilibrium. We're gonna pick up where we left off yesterday. So just say hi in the chat bar so I know that you're all with me. Hey Dylan. Hey Allie. Brianna, Lexi. Hey guys, I miss you. I miss you all. Nice. Okay. Sweet. Alright, round 3, let's do this. We're 3 rounds in. God knows how long this is going to go on for. Alright, so here we go. I left you off when we were talking about equilibrium as being your happy place and what happens when someone takes a big old shit on your happy place. Here is my plan over the next couple of days. I had you work on the first 6 questions of that table. I'm going to do one or two of them with you as review today. And then I'm going to get into temperature and pressure because I want to show you how to do those. If you wrap your mind around concentration, temperature is super easy. Pressure is a slightly different shift that can happen, and we have to talk about that. But otherwise, I want to get through with you how to do those. And then tomorrow night, I need to stream for AP Bio. I haven't streamed for them yet, and with AP Bio I need to do like a longer stream for them, so it's not like I can stream 2 of you in one night. What I'm going to end up doing is tonight, once I finish streaming here, I'm going to pre-record a explanation for all of the questions on that worksheet, like these 1 through 6, and you're going to finish up the remaining, I think it's 12 total, so the remaining 6, you're going to do all them in your notebook, and then I'm going to go through them in a pre-recorded video that I will upload to either YouTube or I'll just post it as a PDQ, and I'm going to give you something pre-recorded. I will explain it, I'll have some extra practice questions in there. I don't know if you guys know how to use Edpuzzle. Otherwise, okay, I was just looking at the sidebar. Okay, I don't know if you guys have ever used Edpuzzle, but what I'm going to end up doing most likely is I'm going to go through the explanations for those questions and then probably pop an ed puzzle question in here or there just to assess that you're understanding. And it's one thing for you to like watch the videos and be like, yeah, I get it. Like I want you to in an ed puzzle where like you have to do it then and there just to see if you're understanding, not graded, just more of an understanding for you and for me that I'm, you know, getting the information to you and you're understanding what's going on. So, there's that. And then the next thing I'm thinking of doing, and it probably won't happen this week, but I'm thinking next week, is I feel like we need to do something fun. Like, we need to do something fun, and it probably should be science and chemistry related. So, the other thing that I'm also entertaining the idea of doing is downloading Zoom, because I know other teachers are using Zoom, and it's more of like an interactive, like, you know, way to participate. Like, we can actually, like, you know, like see each other's faces, and I thought maybe we could play a chemistry version of Heads Up where I can have important terms on index cards and I can put them on my forehead and have you guys try to explain them to me and see if I can figure out what it is that you're trying to say and get the word right. It was just an idea that I had, you know, just a way to do something that's fun and chemistry related instead of it me just being presenting you with content. So I'm just going to wait 30 seconds. Give me the thumbs up that you understand that tomorrow will be pre-recorded. I will probably post that pre-recorded lesson earlier in the day. It won't be like a 9 p.m. pre-record and it gets uploaded. I will try to upload the pre-recorded as soon as possible. So give me a thumbs up on pre-recorded. And then, you know, give me a thumbs up or a thumbs down if you feel like the Zoom idea might be fun. Be like thumbs up Zoom or like thumbs down Zoom. Like, I don't want you to see my face. Whatever. I mean, I don't know, like we're all stuck inside. I thought it would be fun to like see each other. So just give me a thumbs up, you understand both of them. Be like thumbs up pre-record, like put that in parentheses, and then give me a thumbs up for the Zoom or a thumbs down for the Zoom. Let me know what you're thinking. Okay. Thumbs up. Yes, Zoom. Nice. Yeah, I figured that might be fun. You know? Yes, pre-recorded. Yes, Zoom. Cool. Alright, so I have to figure out how to use Zoom. Okay. Alright, cool. And by the way, I just want to share another funny thing with you before we get into chemistry. My daughter, I won't lie to you, like I try to limit the amount of screen time that goes on in my house, but you know, in Corona Chronicles 3.0, like it's not a proud moment of motherhood, but I let my daughter watch, you know, some things on YouTube today, you know, like kid things. But there was a lot of YouTube watching that went on, and my daughter searched my name on YouTube, and she has been asking me for like the past, I don't know how long, if she can have her own YouTube channel. And I'm like, what are you possibly going to stream about? And she's like, my American Girl dolls, like my favorite JoJo Siwa bow. And I'm like, no, you're 6 years old. You're not allowed to have a stream. I'm so sorry. So she found me on YouTube today, and she was very upset with me. She wanted to know how come I was allowed to have a stream, but she is not allowed to have a stream. I had to explain to her, you know, that my stream is completely educational, but if we do a Zoom, she might want to say hi to all of you, because she really wants to be recorded on the internet. So let's do this. Let's get into LeChatelier. Here we go. All right, so the first thing I want to tell you about this worksheet is that there is something called the K, which is an equilibrium expression, and we don't touch K with a 10-foot pole in this curriculum. So on your worksheet that you printed, because you were supposed to print it, you're going to cross off this column, because we don't do K. If you were in honors or AP, they would be talking to you about K. K is not necessary. Okay. Then, the next thing that we need to talk about is we then need to talk about what these little slashes are about. So, the reason why these slashes are here is not because they're not increasing or decreasing, but that was the initial stress. And if I read this table is telling me, or if I read this equation, there's a double-sided arrow, which means this system was in equilibrium. Like, the concentrations were constant, the rate of exchange was equal. Oh no, somebody stressed the system, and the stress that was applied was somebody came along and added nitrogen. So I'm going to put this over here, because this is the poop. Like, this is the LeChatelier moment. Like, oops, I shattered. This entire system was in equilibrium. Well, now it's not, because I shattered on the equilibrium. LeChatelier is like, Let's actually shrink you down because I really like you. I like you looking over my shoulder when I do stuff. Okay, LeChatelier is all like, oh, look, I shot it on the system. And he applies this stress. And this is the stress that was applied. That's the reason why the slash is here. The slash is the stress in this question. So I put the steps over here. I'm just going to raise the steps. And I'm going to do number 1 with you. I think we might have done number 1. We're going to do number 1 again. Obviously, the answers are here, but I'm going to explain how we got it. And then what I'll do is I will do number 2. I will do a remove. And then I'm going to leave the rest of these for you to see in the pre-recorded lesson tomorrow, where you'll see the answers and how that happened. So step number 1, I'm going to color code as I go. Cut the reaction on the arrow. So actually, can I pull this? Can't do that. Cut the reaction on the arrow. Assign the initial stress. Well, LeChatelier, when he took his little shot on the system, decided to add nitrogen. So I'm going to have more nitrogen in my system. That is the adding arrow, so like I'm increasing the concentration. Moving on to the next step, well, the opposite side of the equation, I'm going the opposite side, and it is going to receive the same stressor. Now over here, this is where I need to go with you today. This is an energy term. We're going to treat an energy term the same exact way that I would have treated anything else if this had been, product or reactant. It's just another product or another reactant. If this upsets you, because it's like a whole bunch of numbers, what you have my permission to do, and actually, I'm going to type this, and I'm going to put this over, shrink this guy down, I'm going to type this, and I'm pretty sure that I can I not do that? I don't think I can do that. Hold on a second. Lie. Okay, I am going to make a box. Nope, that's a circle. That is not a box. Box. Yeah, buddy. Okay, and I'm going to block this out. So I'm going to fill properties. I want to fill this with white, so it's gone. And I am going to write the word energy here. That is so not the right size, but I'm going to shrink it down to fit in that little box. Okay, I'm going to put the word energy in here because it's the energy term. Like that, it doesn't matter how much energy, but I'm going to treat energy the same exact way that I would have treated any other reactant, any other product, and in this case, well, energy is a product as well. So when I go to assign my opposite side of the equation arrows, I'm going to assign everything on the opposite side the initial stressor symbol. So like this goes up, and this also goes up. And I just want to take a moment to talk about this. The way no, I'm going to do it in the next one. Yeah, I'm going to talk about my moment and my analogy. All right, so moving on to step number 4. Everything that's left over in the equation, like whatever's left, is going to get the opposite sign arrow. So like this guy goes down. I just assigned all my arrows. I'm going to take a minute. I'm going to pause. I'm going to look right now at the side chat and just give me like the thumbs up, thumbs down to make sure you understood everything I did in 1, 2, 3, 4. Okay, so Dylan says, why does energy get an arrow up even though nitrogen is not present? I think now might be time for my other analogy really quick, Dylan. So bear with me 1 second. Let's say that I was making a recipe, and in order to make my recipe, I need eggs and flour because I am going to make cookies. And cookies produce crumbs. I, again, probably should be typing this, but I'm getting wild. Okay, so this is a disgusting recipe of how to make cookies, but just pretend for a second that all I need to make cookies is eggs and flour, and it produces cookies and crumbs. And right now the recipe is calling for eggs and flour. Well, if I go to the store and I pick up more eggs from the store, like I go to the store and I buy more eggs. If I buy more eggs, theoretically, I should be able to make more cookies and crumbs, because that's the product that's being made. Anything that's on this product side, when I stress the initial side of the equation, the reactant side, if I have more reactants, I should be able to produce more products no matter what they are, cookies and crumbs. In that other little story over here, I have more nitrogen, but I should be able to make more ammonia and energy, because every time I make ammonia, I release energy at the same time. Just like if I make cookies, like I have eggs and flour, every time I make cookies, like I produce more crumbs at the same time. Like cookies are not crumbs. Like I understand like crumbs like are cookie particles, but that's like a part of the analogy doesn't exactly work, but it's the same concept that if I'm making more cookies, I'm also going to make more crumbs because it is also another product of that process. Dylan, take a minute and just wrap your mind around that and tell me if that sounds good. Good, Dylan? Okay. Okay, so I'm going back one more time. I'm just looking at the comment bar and I'm looking at what's going on here. All right, so Audrey says, so everything on the other side will do with the... Yes, Audrey, if I have more eggs, then I should be able to produce more of whatever it is than I am making on my product side. Yeah, that is just that it's kind of like I have more starting materials, and if I have more starting materials, I can make more of whatever it is that I am producing, whether it's cookies and crumbs, it's ammonia and energy. It might be like NaCl and, potassium iodide. It could be whatever is on the product side. All right, looking over here one more time at the sidebar chat. All right, a lot of ridiculous things going on over here. All right, and then Alexa says, the last column says remain the same, but in this it's going up. I need to go back to that table, because Alexa, what I think you're referring to is the K in the last column, and we don't discuss K in this class. K is something called the equilibrium expression, and if we were an honors or AP, we would be doing math, and I think that's what you're referring to. I am completely ignoring the column that says K. K is not energy. I don't want you to confuse the two. Energy is something completely different. It is not K. So I'm just going to look really quick. Alexa, give me the thumbs up that you realize that that was not the same thing. Okay, good. All right, so the next thing that I'm going to do is step number 5. I'm going to evaluate the overall change. So the side that experiences the largest percentage increase. So like on my left-hand side, the hardest part of this is knowing your left from your right. So this is the left-hand side. I have 2 arrows, one up, one down. So that's like half up, half down. So that would be like a half increase. Over here, I have 1 up and 1. I was like 2 of them are going up, like 2 out of 2 are increasing. I experiencing the larger change on the right hand side, which is the reason why we would shift right in this story. Okay, do we understand what happened in everything in the first row? I'm making the executive decision. I'm not going to do number 2. I want to do number 3 with you, and there's the reason why I want to do 3. Okay, give me the thumbs up that we're on the same page. Okay, I'm waiting for a couple more thumbs up just to make sure we're good. Okay, if you're not good, you should tell me. Alright, great. So let's move on. Okay, let's talk about the ammonia shift, which is number 3. I'm just going to clean, because every time we do this, we need to start with a fresh equation. I'm going to start off one more time, cut the reaction in half, and then I'm going to add ammonia. So this one's a little bit different, because my initial stress is not on my reactant side. My initial stress is actually on my product side. So here I go. I have more ammonia. And because this is a reversible reaction, that would mean that I can produce more hydrogen. This actually should be green. Okay, I can produce more hydrogen, and I can also produce more nitrogen. Okay, that's the opposite side, gets the same initial stress. Well, if I have more ammonia, then I can make more of whatever it is on the other side of the equation. Step number 4, everything left over is going to get the opposite sign, so those roll up, which means the energy is going to decrease. And what this means is that every time I make ammonia, every time I have more ammonia, and every time I make these two things, I have to consume energy in that process. Like, I got to use the energy. That's why this is going down. I'm going to evaluate the overall change, and on this equation, the largest percentage increase that I am seeing is actually on my left-hand side. The amount of ammonia would have gone up, the amount of hydrogen would have gone up. The ammonia is my initial stress, and if there was a column for energy, which there's not, then the energy value would have gone down. Take a minute, pause, and tell me we're on the same page. Okay, moving on. Okay, so the first 2 shifts that we did were both increasing, which is the reason why I want to go to shift number 4 with you. And I want to go back to this story really quick. Okay, I'm making cookies. And the world's worst recipe, egg and flour, makes cookies and crumbs. But I want you to pretend for a second that I have everything I need. I have everything that I need in my pantry and in my refrigerator. I have enough eggs, I have enough flour. But like, my kids decide that for breakfast they want eggs, and they eat half of the eggs that are in my refrigerator. Well, if they eat the eggs that are in my refrigerator, that's a problem. That means that I can't make as many cookies. And there's going to be less crumbs, because I don't have as much starting material. Now, this is where things get a little bit trickier to wrap your mind around. That's why I want to start with this simple, equation you might understand from real life. If I lose some of the eggs that I had, I can't make as many cookies and I can't have as many crumbs, which means that I'm going to have excess flour. I don't have more flour. I just have excess flour that I would have used, but I can't use because I can't execute the recipe as many times as I initially would have. I have leftover flour. That is the reason why this arrow is going up. It's not necessarily the concentration's going up. It's just that I have extra of something that I would have used that I'm not using anymore. Give me like 2 seconds, thumbs up on this little story before I take you to the chemistry version. Give me a thumbs up that you wrapped your mind around that. no tomfoolery. I'm just looking at your comment on the sidebar. Van der Waals forces, they're very weak and unattractive. Can't use those to climb up a wall. Okay. All right, so I'm happy you're wrapping your mind around this. Let's go back to the chemistry version. Let's go over here. So I'm going to go back to this chemistry version. I'm taking a look at number 4. So I'm going to cut this reaction in half one more time. Cut the reaction. I'm going to assign my initial stress. Now this question's a little bit different because my initial stress is a removing, like I'm taking away. I have less nitrogen. And if there's less nitrogen, that means that less ammonia will be produced and less energy will be released in that process. Go to the opposite side of the equation. And on this side, I'm going to assign the opposite arrow, and what this means is I have extra hydrogen that I would have used, but I'm not using it, so I have leftover hydrogen. I'm going to evaluate the overall change. I'm looking at this side. I got half down, half up, which would be like a 50% increase. And then on this side, I got both down. So like nothing's increasing on this. That's supposed to be 0. Nothing is increasing on this side. So when I assign, or I am looking for which side is experiencing the larger change in this little story, the number 4, I would actually be shifting to the left because I am experiencing a larger increase. It's a 50% increase, which may not seem large to you, but that's better than a no increase. Like there's a 0. I'm not experiencing a large change on this side. And if I start assigning, well, the changing of ammonia, nitrogen, I'm removing it. That's my initial stress, so that's a slash. I have an increase in hydrogen, so that's increasing. And the ammonia is decreasing. Take a minute, wrap your mind around that, and just give me a thumbs up that we're on the same page. Okay, Jordana just asked, why wouldn't we move to the right if it's a 100%? Now, here's the thing. Jordana, it is a 100% similarity on the right-hand side, but I am always looking for step number 5, the side that experiences the largest percentage increase. Yes, they have the same 100% directionality on the right-hand side, but that is a 100% directionality of going down. Like it's decreasing on that side. So I am looking for the side that is experiencing the largest positive change. Give me the thumbs up that you're good on that one. Jordana. Good. All right, so I'm going to leave the rest of these for the pre-recorded stream, and I'm going to give you the rest of the answers then with more of an explanation with some extra practice. What I need to do today, and I have about 15-20 minutes to make this happen, is I need to get into a temperature shift with you. So the way that this equation was presented to you yesterday, that's a lie. The way that this equation was presented to you yesterday was I only had the reactants, which means I took something out, and I'm actually going to ungroup this for a minute because I had this hiding. There was an energy term here. This is your delta H. And we had this conversation on Friday, which feels like forever ago when we were last in person, but if the delta H is negative, this means that energy is being removed, energy is being released, energy is a product in this equation. So if I had to rewrite this for you, the way this would actually look, no, not what I meant to do. The way that this would actually look is like this. I actually want to group you. No, I don't. I just want to copy and paste you one more time. If I were to take this delta H out, it's important, it's a good piece of information, but if I wanted to incorporate this into my equation, it would actually look like this, where I would have the energy term on my, let me get the word in here too, on my product side, because that delta H is an exothermic delta H, it is negative. So I'm actually going to group these. Group. No, you don't want to behave. Group. I just have to retype you in. Let's get you in over here. Okay, so the word energy would be, this is ridiculous. Come on. Okay, so the word energy would be over here, and energy would be a product in this equation because the delta H is negative and it's being released. It's an energy term. Don't be fooled, like not all energy terms have to be a positive delta H. I think it's this slide. Wait for it. Nope, it's this slide. Okay, in this slide over here, I have a completely different equation. And in this equation, the delta H is a positive delta H. Like this is from table I. I'll show you how to find that later, but this is a positive value. And if it's a positive value, well, that would mean that the energy is being added. The energy is being absorbed, which means that that energy term would actually be on the reactant side. And I'm going to get to the slide and we'll do a shift with this guy later. I'm just showing you for reference purposes now. But because this delta H is a positive delta H, it implies it's endothermic, which means the energy would have to enter the chemical system as a reactant as opposed to exit exothermic style as a product. So when I was showing you these equations yesterday, I wasn't necessarily 100% honest with you that there was an energy term. Now there's an energy term. And if there's an energy term, it allows you to stress the equation using temperature. I'm going to treat this the same exact way, and I'm going to use the same exact steps that I used before. So I'm going to copy and paste these steps in. You don't have to copy and paste them in your notes. You can just add. I'm going to cut the reaction on the arrow. Same situation. I'm going to go red, cut the reaction in half, and I'm going to assign the initial stress. Well, I could add, which would be an increase in concentration, remove, decrease, but I'm going to throw in here, there should be like an additional little part of this step in number 2, that if I am changing temperature, so a temperature stress, I am going to stress the energy term. And I am going to stress the energy term the same exact way that I stressed before. If it's an increase, then it's going to be an up arrow. If it's a decrease, then I would put a down arrow. Okay, LeChatelier comes along. This equation is equilibrium. These little arrows are equal but opposite. Everything is concentration constant, rate of exchange is equal. Well, LeChatelier comes along and he goes, oops, I shattered. I took a big old dump on the equilibrium, which means I stress the equilibrium. And the way he's stressing it, he goes, oops, I shattered. I increase the temperature. He takes a shot on the energy term, because this is where stress is applied when you are changing the temperature, because temperature is a form of energy. It's average kinetic energy. This is where the stress is applied. So I'm going to put the little poop back. And I'm going to stress this the same way I did before. I'm going to treat this like any other reactant, any other product. I'm going to increase the temperature. If I increase the temperature and I have more of this material, theoretically I should be able to produce more nitrogen and more hydrogen. And in that process, I am going to consume the ammonia that I was using, you know, that was on this side of the equation to make this stress work. Take a minute. I'm going to pause. I'm going to take a look right now at the side chat bar, and I am looking to see, to make sure you understand. Please take a minute and give me the thumbs up, thumbs down that you understood this concept of stressing temperature and where that needs to happen. Give me thumbs up or thumbs down. So the next thing I would do here, or the final thing would be, I would have to check and see which side is experiencing the larger increase. And based on these arrows, I would be shifting to the left because there's a larger percentage increase. I'm going to have you take a minute and I want you to try it all by yourself. What would happen if I decrease the temperature? So I'm going to put the energy term in and I want you to take a minute and I want you to do the shift. I am 30 seconds ahead of you. So I'm going to pause for like 20-30 seconds, give you time to do this, and then I'm going to work through this and see if your work looks like mine. Hold on 1 second. Okay, check your work and see if your work looks like mine. I would say once I assess this left versus right, that this system would shift to the right because there's a larger change on the right hand side. Give me the thumbs up to make sure we're all on the same page. Okay, good. All right. So the one thing that I just want to point out is that people then generalize that every time I have a temperature shift, if I increase, that an increase would shift to the left. Like that's what happened over here. And that was an increase. Whereas if I decrease the temperature, everyone's like, oh, that always shifts to the right. That's not always the case. Like it just so happened that in this equation, the way that this is written, because this is exothermic, the energy term is a product, which means I'm shifting on the product side. It doesn't have to be that way. You can have a positive delta H, which means that the reaction is endothermic, which means the energy term is on the enter side. And let's do a shift with a endothermic reaction really quick. Let's stress this endothermic reaction and let's stress it with a positive increase in temperature. So let's copy paste this in. Let's stress this equation. Let's stress this equation and let's increase the temperature, which we're not going to get the same answer. Take a minute, not even, take 30 seconds, stress this equation by increasing the temperature, and check your work. I'm going to give you about 30 seconds, and then I will do it and see if your work looks like mine. Yes, Jordana. Okay, see if your work looks like mine. I'm going to apply my initial stress of energy, which means that I'm going to have more product that will be made, and I will consume the nitrogen and the oxygen in that process. And if I'm looking at overall change, this side versus this side, you may say like, oh, well, they're both like 1 arrow and 1 arrow, but there's only 1 arrow here, and that's like 1 out of 1, which means that's like 100% increase. Like everything is increasing on the right hand side. Where on my left hand side, I have 1 arrow, but it's not about the number of arrows exactly. It's about the percentage comparatively. So like this one's going up, but these two are going down. So I mean like 1/3 of these is increasing, as opposed to we got 100% increase over here. This equation would shift to the right. Okay, take a minute and give me thumbs up and let me know that we're on the same page here. Okay, Jordan says, I don't understand why nitrogen and oxygen are decreasing. Okay, so let's go back to this story really quick. I'm going to add an ingredient to this. So I have eggs and flour. Oh, can I ungroup you? Oh, no. Oh, what? What? I can do that? Wow, that was really impressive. I had no idea I could do that. Okay, let's go eggs. Let's go oil. And flour makes cookies and crumbs. And I'm going to get rid of all these arrows in a minute. Okay, again, not the best recipe for cookies. They'd be disgusting, but you get the general idea. So let's go back to this story. I went to the store and I bought eggs, I bought flour, I bought oil. I have everything I need to make cookies, and I have, you know, everything I need in terms of quantity. Well, my kids come along. That's a lie. Okay, I go to the store and I buy more eggs. So theoretically, if I have more eggs, I should be able to make more cookies, and I should be able to make more crumbs. But when I went to the store, I didn't pick up eggs. That's a lie. When I went to the store, all I did was pick up eggs. I didn't buy oil. I didn't buy flour. So I'm going to have to use whatever it is that's in my pantry. Like, I should have been able to do this recipe 5 times. Now I'm going to do the recipe 10 times. And if I do the recipe 10 times, I am dipping into and I am using more oil than I intended. I'm using oil that I had on reserve that I am now, you know, consuming in this process that I had in my pantry. Like I wasn't supposed to use it on those recipes, but I'm doing more of those recipes, so I'm going to consume more oil in that process. When I went to the store, I didn't buy more flour. Like, I am going to use whatever flour was in my pantry. I should have been able to do that recipe 5 times. Well, now I have more eggs. Well, guess what? If I'm using more eggs to do this recipe 10 times, I'm going to need more flour in that process. So this would be like the not chemistry example. If I go back to this example, when I have more energy, I can produce more nitric oxide. Like that's what happens. But because I have more energy and I am doing this equation more often, I am going to use whatever nitrogen and ammonia I had, and I'm going to start dipping into that reserve. Jordana, does that make sense to you? Just give me the thumbs up that would make sense. Okay, so I'm going to go back to Alexa's question really quick. And you're asking really great questions, and I'm going to try to make this as simple as I possibly can. Let's say that the recipe that I need calls for 1 egg, 2 cups of flour, that's a lie, 2 oils, and 2 cups of flour. And in my pantry, I'm going to lie, I'm totally lying. In my refrigerator, I had 5 eggs. But in my pantry, I had like 25 cups of oil, and I had like 25 cups of flour. I have extra oil and flour like laying around. Just because it's there doesn't mean that, let me rephrase that. Just because I'm not using it doesn't mean it's not necessarily there. It's just that I'm not using it to execute the recipe. Well, in this recipe, I need 1 egg, 2 oils, and 2 flours. If I have 5 eggs, I could do this recipe 5 times. I'm gonna have extra oil and flour in my pantry that I was not planning on using that day. Well, let's say I go to the store, which, by the way, let me actually do math on this for you. That would mean I need like 10 oils and I would need like 10 flours, which means I would have like 15 extra. Let's actually do math here. So there would be like 15 extra in this story. So if I go to the store and let's say that I bring home 5 more eggs, which makes this total now 10 because I added more eggs to the story, that means that I can do this recipe 10 times. And if I do it 10 times, I'm going to need 20 oils. I'm going to need 20 flours. But I had enough to do that, but the amount that I have left over in my pantry is not 15 anymore. It was 15. But now, in comparison, after I stressed the system, I only have 5. Like, I had 15 extra, now I only have 5. That is that number. Alexa, take a minute and tell me if that makes sense to you. Okay, good. All right, so I have one more type of shift I have to do with you, and this is quick. Our pressure shifts. So if you wrapped your mind around temperature and you wrapped your mind around concentration, then these shifts are super easy. When you are talking about pressure, your equation must have gas in it. So I am going to, actually that's a lie. I'm going to go up with this. You need gas because gas is the only phase of matter that is going to be affected by pressure. I'm going to grab my steps and I'm going to bring my steps in. So bring my steps. Okay, so I cut the reaction on the arrow. Same exact way. Okay, so I am going to assign the initial stress. I am going to decrease the pressure. When I assign a pressure shift, when I assign a pressure shift, I need to look for gas. It only affects gas. So I need to look at my phases of matter. So I go over here and I go, is nitrogen a gas? Yep, nitrogen is affected by this pressure shift. I am decreasing the pressure. So nitrogen would get a down arrow. And then I'm going to go, keep going and go, well, is hydrogen a gas? Yeah, well, this is a phase, this is gas too. So this is also affected by, pressure. And then I'm going to go over here and go, well, this is a gas. Well, this is also affected by pressure. And then you might say, well, I don't understand because all the arrows are the same. Like, it would always be that kind of situation where I'm looking at these arrows. When I do a pressure shift, I'm not going arrows. I'm looking for gases. And I am going to say, this is affected. This is affected. This is affected. All these are affected. If I go arrows, I'm not going to get one side favored over the other. So when I assign my initial stress, when I'm doing gases, I am just going to do a check. I'm going to go looking to see if gas is present or not, and then make checks and be like, yep, yep, yep. I'm going to have to add a little subset of steps over here, because gas gets a little bit different of a method for handling the shift. So, new text box. If it is a pressure shift, and I'm going to shrink this down, if this is a pressure shift, then step number 2.5, because this is gas, so 2.5, and this is only true for gas and pressure. And I need to shrink this down a little bit more. Shrink this down. I need to start counting the number of moles of gas on each side of the equation. I have to start counting. So right now people would be like, oh look, like I see 2 on this side and I see 1. But that's not what they're asking you for. They're not asking you for the identities. They're asking you for the number of moles. So I need to go back and I need to take a look at the mole ratio, which is when this thing is balanced. And I need to start counting the mole ratio. What number is implied is written here, even though there's nothing written. That's like a math thing. Like if I say X, how many X's are here? Nothing's written. There's 1 of them. But I would not ever write 1x because that's redundant. In chemistry, it's the same concept. If there's nothing written, it's implied there's a 1. If there's more than 1, I would need to write that, which is happening here. I have 1 nitrogen over here, and I have 3 hydrogens, which makes this grand total on this side 4. Then I'm going to go to this side, and I'm going to say, well, there's 2 moles of this ammonia stuff. So I have 4 versus 2. I'm going to take a minute and pause, and I want you to tell me if you understood how that happened. Give me a thumbs up. The counting of the moles. Go ahead, Jordan. Yes, Audrey, they're going to have to tell you clear as day that it's a pressure shift. They're going to say to you the pressure is increasing or the pressure is decreasing. Okay, Jordan, what's your question? Okay, so once I count up the number of moles, this is where you have to remember a concept that we learned about earlier in the year. This is all about gases. So we want to go back to the whole concept of what makes a gas ideal. And if we have an ideal gas, we want to have a high temperature and a low pressure. That is ideal. And when I think of ideal, I think of myself on summer vacation. I think I'm sitting on the beach. Like, the temperature is beautiful out because it's summertime. The temperature is really high and the pressure is super low because, you know, we finished the school year. Like, you know, we finished Regents exams, AP exams are over. Like, it's low pressure. I think of being on the beach during summer vacation. That is the most ideal time of the year, I think, for like anyone. I think of the vacation theory. So this is a pressure shift, and I'm not interested in temperature. It's not a temperature shift. We did temperature before. It's this, low pressure. This is the most ideal. So if I am going to start counting and I look and I say there's 4 versus 2, then I'm going to go, well, I'm going to go back to the shift and I'm going to ask myself, is this ideal? Is a decreased pressure ideal? Well, an ideal pressure would be a lower temperature. If I drop the pressure, that's definitely more ideal. If I drop the pressure, I am going to shift to the side with the most amount of gas. No. I need to pause for 1 second. I just had a complete brain fart. Don't write that down. Hold on. You gotta forgive me. Give me 1 second. Yes. Yes. Okay. I'm so sorry. It's been a really long day of my kids screaming and yelling and painting and leprechaun traps. I'm so sorry. If I decrease the pressure, that is more ideal. I am going to shift to the side with the most gas because that is ideal. Okay, give me a thumbs up that we wrapped our mind around that. That I'm looking at this is like from the standpoint of ideal, and if we're ideal, we favor the side with the, you know, let me rephrase that. An ideal gas, we would want low pressure. So if the pressure is decreased, that's pretty ideal. I'm going to favor the side with more gas because that's like, for gases, that would be a more ideal condition. So if I were to look at this is 4 versus 2, I'm going to find the side that has more gas, and that is the side that I am shifting to. And in this little story, this has more gas on it. I would shift to the left-hand side because there is more gas and a low pressure would be most ideal. More gas. Give me a thumbs up on that. Okay, moving on. So I'm going to do the last shift with you for pressure. Let's do an increased pressure shift. I'm going to start off the same way, cut the reaction in half. This is 4, this is 2. And then I'm going to ask myself, is increasing pressure ideal or not? So like ideal or not? and again, probably should be typing, but I'm getting lazy, ideal or not, increasing the pressure is not ideal. I am going to favor the side with less gas. Increasing the pressure, not ideal, favor the side with less gas, and in this case, I would shift to the right in order to accommodate this stress. Okay, there's one final thing that can be done in terms of LeChatelier, but I think tonight we're going to call it, just because there was a lot of things that happened here. We reviewed concentration, we talked about temperature, we talked about pressure. I will, in the pre-recorded, talk about a catalyst shift with you. There's not really much that goes on there, but there is something you should be aware of. And what I will do is I will post to the website the pre-recorded, because I have to stream for AP Bio probably tomorrow. Hold on. I'm going to stream this 1 through 6, and I will go through the answers and have in an ed puzzle some practice questions for you that will be like, you know, embedded inside that you'll do just to make sure that you understand. And I'm going to add the remaining set of questions, which I think is 7 through 12. I posted on the website that you're going to be finishing this worksheet 7 through 12, and then I also posted for you a POGO on equilibrium with LeChatelier's principle. I'm going to ask that you print that. It's a really good review. Print, complete, hold on to it into your binder until I see you all again. I think that this is the time where we call it a night and you digest all the information. I will post sometime tomorrow the pre-recorded lesson, and then I think I'll probably have one more stream to tie up loose ends on Friday. Come up with something that you guys should work on over the weekend. I won't be streaming over the weekend, but I will give you some things to think about, work on, and maybe we can have our heads up Zoom and have a little bit of fun practicing some chemistry together, maybe over the weekend. Or maybe even next week. So I'm gonna just call it a night here. Take a minute for me. Oh wait, I see something. Hold on. Putting my glasses back on. Okay, on the chart. Okay, on the chart, under the increased pressure and decreased pressure, how should we write it in the boxes? Like if they are increasing. Okay, so actually all the arrows would be the same. All the arrows would be the same, so if I increase the pressure, all of them go up. But that's the reason why you have to go count the mole story, because if you go just based on the number of arrows, you're not getting an appropriate shift. If you're decreasing, all of them would be decreasing, but that's the reason why you can't go all of the arrows to give you the shift. That's why you have to go the count the mole method. Okay? Good? Alright, give me the thumbs up to make sure we're on the same page. Okay, I'm gonna call it a night. Okay, Audrey, it's not that they're going to tell you that it's an ideal gas or not. You have to know the conditions that are ideal. So I'm just going to go back here for a minute. I'm going to go back here. And I'm going to... Do I clean this? Let me clean this. Okay. You have to go back, and I'm just going to slide the steps down and out of the way for a minute. You have to go back. And in order for you to make that decision, you need to go back and you need to take a look at the initial shift. And you need to go, oh, like the shift that happened, it was a decrease in pressure. And you are the person who needs to make the decision, like, is a decrease in pressure ideal? Or is that not ideal? Like, this is you. You need to know that. Like, ideal or not ideal? And I'm not typing ideal. I've decided, yeah, I'm going to type it. Okay, is this ideal or not? That is your decision-making process. And if you understand the concept of the vacation theory, well, if you drop the pressure, that's not ideal, then you need to say if you decrease the pressure, that is ideal. Like, that's the whole vacation theory. if it's ideal, I favor the side with most gas. The most gas is ideal. And then if I flip this, and they're going to clear as day tell you in the problem, they're going to go, oh, I increase the pressure? Well, you need to make the decision, is that ideal or not? If I increase the pressure, that's not ideal. I favor the side with less gas. So not ideal, less gas. Okay, good. Alright, cool. Alright, I'm going to call it a night, and I will see you all. I'm going to pre-record tomorrow, and I will shoot you a text and remind and let you know that when we'll do this again. Alright, I will see you all another time. Stop streaming. Have a good night and stay safe.